I am Padmaja Gaikwad from the Department of Computer Engineering, Terna Engineering College. Today I will present my project on 8-bit BCD addition under the guidance of Dr. Vishwajit Gaikwad. The aim of this project is to perform addition of two 2-digit BCD numbers on the 8086 microprocessor. The program accepts input from the keyboard, adds them using the DAA instruction, and displays the sum on the screen using DOS interrupt. In BCD, each decimal digit 0 to 9 is stored in 4 bits, a nibble. In this project, I use packed BCD, where 2 digits are stored in a single byte. High nibble is stored in tens digit and low nibble is stored in ones digit. Now, why do we need DAA? When two BCD numbers are added in binary, the result may not be valid BCD. It is an 8086 instruction that corrects accumulator lower after a BCD addition. It only works on AL and uses the status flag set by the previous ADD or ADC. If the lower nibble is greater than 9 or auxiliary carry flag is equal to 1, then add 06H to AL. If the upper nibble is greater than 9 or carry flag is set to, then add 60H to AL. Now we will see an example here. And the applications are it is used for financial calculations and digital systems requiring accurate decimal arithmetic. To handle input and output, I used int21h functions. Its purpose is to read and write characters and strings from standard devices like keyboard, screen, and it works with registers, accumulator, DL, depending on the function. Each function is selected by placing a function code in AH before calling int21h. Its functions are if AH is equal to 01h, then it reads a character from the keyboard. AH is equal to 02h, it displays a character. AH is equal to 09h, it displays a string ending with $, and AH is equal to 0AH reads a full line of input from the keyboard into a buffer. It does not display anything. Now let us understand the code. Here, I set the assembler memory model to small, which means one code and one data segment. I reserve 0 into 100 bytes, that is 256 for the stack with dot stack 100h. Then I start the data segment with dot data so I can declare messages and variables. These three lines define the string I will print. Each string ends with a $ because DOS function 09h expects that terminator. Note, I use 10,13 line feed. Then carry is written. The conventional DOS order was 1310, but this still produces a new line on most systems. I reserve 1 byte each for num1, num2, and sum. Those are uninitialized. Num1 and num2 will hold the packed BCD bytes for the two input numbers. Sum is declared, but in this program, I don't actually write to it. The final result stays in registers while printing. Now, this begins the code segment. At the labels start, I initialize the data segment moveax, @data. Loads the data segment address into AX and move ds, AX copies it into DS so the program can reference the data labels like MSG1, num1, and so on. LEADX, MSG1, MOVAH, 09H, and int21H. Here, I load the offset address of MSG1 into DX with LEADX, MSG1. Then I set AH is equal to 09H to select DOS interrupt 21H function 09 and call int21H to display. Enter first two-digit number on the screen. Okay, so now while reading first digit, now I read a single character from the keyboard. MOVAH, 01H selects DOS function 01. That is read character, a code, and int21H waits for a key press and returns the ASCII code in AL. For example, if the user types 4, AL will be 0 into 34. Now, SUB EL, 30H and move BL, AL. Convert the ASCII digits to its numeric value by subtracting 30H. That is ASCII code for 0. So 0 into 34 becomes 4 into 4, that is 0 into 04. I then move that numeric value into BL, that is temporary storage for the tens digit. Now move CL, 4 and SHL BL, CL. Here I put 4 into CL and shift BL left by 4 bits. SHL BL, CL. This moves the tens digit into the high nibble of BL. So a decimal 4 becomes 0 into 40. I use CL as the shift count. Shifting by 4 makes the digit occupy the top half of the byte. Okay, now to read the second digit. I read the second character, that is the ones digit, the same way. EH is equal to 01H and in 21H read it into the AL, then sub AL, 30H converts the ASCII code to a numeric value. Okay, so ADD BL, AL, move num1, BL. Now I add that ones digit into BL, which already contains the tens digit shifted. The ADD BL, AL makes BL a packed BCD byte. High nibble is tens, low nibble is ones. I then store BL into memory at num1. Now, to input the second number, I print the second from message 2 in the same way as the first, so the user knows to enter the second two-digit number. I repeat the read, convert, shift sequence while reading the first digit for the tens digit and the second number. After reading and converting the ASCII character, I move the numeric tens into CH and shift it left 4 bits so it sits in the high nibble of CH. Now, while reading the second digit, then I read the ones digit for the second number, convert ASCII to numeric, add it into CH, and store the resulting packed BCD into num2. Now, while performing addition, I move the first packed BCD from memory into AL and add the second packed BCD. This ADD is a normal binary ADD and the normal binary add and the intermediate result may not represent valid decimal digits in each nibble. Immediately after the ADD, I execute DAA, that is decimal adjust after accumulation, to convert the binary result in AL into a valid packed BCD result. It is critical DA is executed right after the ADD because it uses the flags set by the addition. Okay. So we will understand the importance of DAA while running our program. So we will see to that later. Now, after DAA, I check the carry flag with JNC. Jump if no carry. If a carry occurred, it means the sum is 100 or more. So I put 1 into CH to represent the hundreds digit. Then I jump to display. If there was no carry, the code falls through to the no carry label and I set CH to 0, meaning there is no hundreds digit. Note that earlier I used CH to build num2, but we already stored num2 in memory, so it's safe to overwrite CH now. At the display label, I print the message 3 string which says sum is. So the user sees the label before the numeric output. Okay, and here I prepare to print a single character with DOS function 0 to H. I move the hundreds digit value 0 or 1 from CH into DL, convert it to ASCII by adding 30H and fall in 21H to print it. I also move the adjusted BCD result in AL into DH. I will use DH to extract the tens and ones next. Okay, this code prints the hundreds digit even when it's zeros. If you don't want a leading zero, you would check CH and only print when it is 1. This is just an additional note that I came to know. Now, to display the tens digit of a result, now I print the tens digit. I copy the result byte from DH into DL, then mask it with and DL, 0F0H to leave only the high nibble. I shifted right by 4 bits to bring the tens digit into the low nibble. Then I add 30H to convert it into ASCII and call in 21H to print it. Finally, I print the ones digit. I copy the result byte from DH to DL, masked with and DL, 0FH to keep only the low nibble. Add 30H to convert to ASCII and call in 21H to print the character. Now, to finish, I call DOS function 4CH, which terminates the program and returns control to the operating system. End start tells the assembler where the program entry point is. This is the program that I performed and we will perform it now. I will show you, but this is the output that I got. Thank you. I have already written this code in Notepad to save ourselves some time and I have saved it as bcd2.asm and it is saved in this directory. Now we will see how to run the program. So first we will access the file that this is saved in. Now these are the steps to run the program. We have 0 warning errors and 0 severe errors. That is, the program is correct. Now we will link the file. We'll link the obj file as it is created now. And finally, we will run the program. Now I will enter a 2-digit number, another number. Now this is the solution. Here the tens and units, the cursor moves to the next line as the tens and units digit are filled, as it is supposed to be a 2-digit number. Now, if the addition result is less than 100, the carry flag is 0. So the program prints just 2 digits. But if the result is greater than or equal to 100, the carry flag is 1 and it prints an extra digit 1 for the 100 space. So this is how our output looks like. I hope you understood. Thank you so much.